I want to welcome you along with Steve Duckett, our County Extension Director here in Buncombe County, and myself, Allison Arnold, Cooperative Extension Agriculture Agent in Buncombe County. I'll be your host. We want to welcome you to Understanding Climate Change in the North Carolina Mountains, the first of 3 in a series. Our session number 1 is Climate and Weather Made Simple. Our speaker today is Dr. Walt Robinson. He's a professor with the Department of Marine, Earth, and Atmospheric Sciences at North Carolina State University. Today, Dr. Robinson will walk us through Earth's climate history and what that history can tell us about today's climate change. We'll also go over the differences between climate and weather and the effects of each on a warming planet. I'm going to hand it over to you now, Walt. Thank you so much.
Well, thanks very much for having me. And thanks to everyone joining us this evening. Yes, I'm going to talk about climate change, climate history, and segue into some discussion of weather. Weather is a big topic, so I'm going to cover weather in the context of climate change. Let's dive in. Let's start with Earth's climate history. As indicated on the slide, it's been a wild ride. Earth has a very interesting and rich climate history. This is a plot from deep in the past going towards the present. And it's an interesting graph. If you look at it, you'll notice that the time axis changes in its resolution as you go along. There's all kinds of interesting things going on in this plot. It's showing variations of temperature that are estimated from various types of geological information and fossils and geochemical information. It's really interesting stuff. Why am I showing this? One is to show that, first of all, the Earth does have this rich climate history with some really large excursions or variations in temperature. And the temperature variations are shown here on degrees Celsius and on the right-hand side, and degrees Fahrenheit. I'm not going to talk about the whole thing because that would be a whole graduate course, not an evening. I'm going to focus on a couple of things, which are shown by these icons at the top. One is a period actually even before 500 million years ago, a period of very, very cold temperatures on the Earth that we call Snowball Earth. So Earth has been a lot colder than present. There's this period in the Eocene, 50 odd million years ago, where it was a lot warmer. And then over a long period of time, these almost periodic or regular oscillations in the temperatures of the planet that were associated with the advance and retreat of these great ice sheets, what we call ice ages. Let's take a look at those 3 examples pretty briefly and see what we can learn from them. So let's go back to this idea of Snowball Earth. I started graduate school in 1979, and this has all emerged since then. This is pretty new stuff scientifically. What was discovered was lots of geological evidence that there was a period around 610 million years ago. There are actually a couple of episodes like this where the Earth was mostly covered by ice. And there's geologic evidence, dated glacial scrapes or striations on rocks. These interesting features called drop stones. And this is kind of cool. You can imagine a rock falls into a glacier. That glacier or ice sheet goes out into the ocean as an iceberg. Eventually it melts and it drops a rock into the sediments at the bottom of the ocean. You get preserved in the geologic record something that looks like this. They're sort of attractive. What you're seeing is a rock that's been dropped into a sediment layer. Then the whole thing has become a solid rock, become lithified later. Our friends in astronomy tell us that 610 million years ago, the sun was less bright than it is now. Actually, the sun has gotten slowly, ever so slowly, more luminous over the course of the 4.6 billion years of Earth history. But what made this Snowball Earth possible was a couple of things. One is, and this is key to the story later on, there's pretty good evidence from geochemistry and rocks that the carbon dioxide in the atmosphere was a lot lower then. That meant a weaker greenhouse effect, and I'll come back to this greenhouse effect in a bit. The reason for that actually geologically is a lot of the land, we have this idea of continental drift or plate tectonics. A lot of the land before the snowball was concentrated at low latitudes where there's lots of rain falling on the Earth, weathers rocks, and that takes CO2 out of the atmosphere. So there was a weak sun, low CO2, Earth started freezing over, and then we have this idea of positive feedbacks. You start with less carbon dioxide and a weaker sun. More sunlight is reflected to space. That makes the Earth cooler still, lowers the temperature. If it's colder, you have more ice cover, and then you have more sunlight reflected. So you have a feedback loop. These sort of feedback loops are actually important for how the Earth responds to things that either happen naturally, like Snowball Earth, or things that we're doing to the planet more recently. We have these positive feedback loops. So how did it end? Obviously, we're not still in a Snowball Earth. It ended because basically the weathering to pull CO2 out of the atmosphere stopped when it was covered by snow. A colder Earth, there's much less rainfall, less weathering. The CO2 was building up under the ice and then getting into the atmosphere through cracks. There's always CO2 being put in the atmosphere by volcanic activity. So the balance was switched from removing CO2 from the atmosphere to building it up. Eventually, you got a really strong greenhouse warming, and that was enough to counteract what we call albedo feedback effect, counteract a big greenhouse effect, warm the Earth, and take it out of the snowball. So that's one example. Climate really different from now. The players are amount of sunlight that was absorbed and the strength of the greenhouse effect. Okay, now we fast forward to a period much more recent. Actually, I have a colleague, Ethan Hyland, my department, who really focuses on this period. This was a very warm period on the Earth. Ellesmere Island, fossils of this critter, Coryphodon, which was sort of like a proto-hippopotamus, all discovered in an environment that looks subtropical, all the way up in the Arctic, Ellesmere Island. That's showing where Ellesmere Island is. So you have evidence from fossils of sort of warm weather, warm climate animals and plants in very high latitudes. Geochemical evidence that the carbon dioxide was much higher than it is now, 2.5 to 5 times higher. It's not known exactly why. Maybe a spate of volcanic activity put a lot of CO2 in the atmosphere. And so we had a climate that was much, much warmer than today during this Eocene warm period. And my third example from the past are the ice ages. The Pleistocene ice age basically occurred from 1 million in the last, what we call glacial maximum, when there was a lot of ice cover, not in North Carolina, by the way, but over much of North America, down in the Midwest, ended about 20,000 years ago. So there were these ice sheets, these huge ice sheets advanced and they retreated. Lots of evidence of how the climate changed from today's ice sheets, and I'll explain that in a bit, and from looking at records preserved in seafloor sediments. Geologically, this is pretty recent periods. We have really good, detailed, pretty high resolution in time information from this period. So what was the prime mover of these advances and retreats of ice ages? Here's a record, and the one in the middle is temperatures fluctuating, methane, which I won't spend so much time talking about, but it's another greenhouse gas, and carbon dioxide. And this is from an ice core record. One of the things geologists like to do is they like to have time go backward running to the right. So the way you want to look at this record going through time is from right to left. So these descents into cold periods and then rapid warming. This was the last glacial maximum and then rapid warming into the current non-ice age climate. You can see there's sort of a cycle to this. It was suspected all the way back in the 19th century. This had something to do with fluctuations in Earth's orbit. Earth's orbit is pretty complicated. It's an ellipse. We have seasons because the Earth tilts on its axis. That's called obliquity. How much it tilts varies over time. And then there's this concept of precession. We know where the North Pole points right now. Our axis of rotation points to the pole star, the North Star. But we know that wasn't true in the past. So a top will do this precession thing. Before computers, it took a really good mathematician, this fellow Milutin Milankovitch, to do a really good calculation of how the distribution of sunlight at different times of the year, the strength of sunlight, different times of the year, different places on the planet, varied over thousands of years. And he did that calculation. That was the mathematics. But his insight was that what really matters is how much sunlight falls at high northern latitudes in the summertime. And in high northern latitudes, there's land at high latitudes, not the Arctic Ocean, but still at high latitudes, Alaska, subpolar Canada, Siberia, et cetera, high latitudes of Europe. If it's cold in the summer, ice, snow that forms in the winter can survive over the cold summer and not melt. And then the next year, snow builds up on top. And over time, you create layers and the snow builds up and compresses, becomes ice and you form glaciers and ice sheets. So that's all about sunlight and Earth's orbit. Where's the CO2 piece? Well, there are these big fluctuations of carbon dioxide that was discovered around 1980 or so. People found that in these ice sheets, the ice sheets that survive today in Greenland and Antarctica, there are bubbles in the ice, and those preserve the atmosphere, sealed away what the atmosphere composition was like tens of thousands of years ago. And they made the amazing discovery that in periods where it was colder and there was more ice cover on Earth, carbon dioxide was lower. At the same time, the climate modelers were just really getting good with their climate models. And they had this Milankovitch idea of these orbital cycles, and they put that into their climate models, and their climate models would just not make a good ice age. So they were wondering, either the models are wrong, Milankovitch is wrong, what's going on? But then as they confronted this problem, they learned about the people taking these cores of ice out of Antarctica and Greenland and finding out that CO2 was much lower during these ice ages. And when they reduced the CO2 to these low values that were found during the ice ages, their models were able to reproduce an ice age. So this was an interesting case of observational science and theoretical science meeting up and solving what was really a perplexing problem. There was a lot of excitement. I was in graduate school at the time when this happened. So you could ask, does carbon dioxide cause the ice age, or does the ice age cause the change in carbon dioxide? And the answer is it's both. It's a feedback, again, a loop. And it's interesting. We know how carbon dioxide causes climate change, and I'll get to that in a minute. But we still don't know very well the other piece of this, how these variations in climate associated with these advances and retreats of glaciers, how that causes CO2 to change. That's still an active area of research. So when you put those three examples together, there's sort of two big ingredients that make Earth's climate change and fluctuate over geologic time, a recipe, if you will. And those ingredients are sunlight. And the amount of sunlight, it's not just how bright the sun is if you're looking up, it's how much stays in the Earth's system, how much is absorbed, not reflected. And that can be changed by how bright the sun is. It has changed slowly over the history of the Earth. It changes a little bit, a very little bit with sunspot cycles. But then the things that happen on the Earth change how much sunlight is absorbed. Clouds reflect sunlight, or at least most do, and more snow and ice will reflect clouds. So sunlight is one ingredient. And the other are these changes in the greenhouse effect associated with a bunch of gases. I've listed them there. Water vapor, the gaseous form of water, is an important one, but that one is part and parcel of the climate system. As you know, if the temperature is higher, all else equal, there's more water vapor in the atmosphere. The things that vary because of what we do or geological processes do are these others: carbon dioxide, methane, nitrous oxide, and then these are things like freons that humans produce. But the big one that we put in the atmosphere is carbon dioxide, and that's the one that's fluctuated importantly over Earth history. So what that does is it modulates the greenhouse effect. You could spend a lot of time on this. I'm just going to do this briefly. Earth is an energy balance. Sunlight comes in. Some is reflected by clouds and ice, snow and ice. And there's this other type of radiation called infrared radiation, long wavelengths. And that's given off by warm objects like the surface of the Earth. But some of it is absorbed by the atmosphere, by these gases. And some of that radiation then is re-emitted or sent back down to Earth's surface. And that's this downward arrow here. That makes the Earth a lot warmer than it otherwise would be because these gases are in the atmosphere. That's the greenhouse effect right now, right there. Basically, this arrow of energy of infrared radiation coming downward from the atmosphere, that's the greenhouse effect. The greenhouse effect is a really good and important thing. If there were none of those gases, no water vapor, carbon dioxide, et cetera, in the atmosphere, the average temperature of the Earth would be below 0 Fahrenheit, and we wouldn't be here. It would be too cold to support life. If you take the natural greenhouse gases, and natural, of course, is varied over Earth history, but we could say natural, maybe recent natural, like 1800 or something, composition of the atmosphere, natural greenhouse gases trap this infrared radiation, send it back to the surface, create a nice greenhouse effect, and warm the average temperature of the Earth to something around 56 degrees Fahrenheit, which is pretty pleasant and sustains life. So without the greenhouse effect, we wouldn't be here, and Earth would not be. This is sort of a silly picture. If there was no greenhouse effect, there would be no houses and no trees. So what about the additional greenhouse effect? Where does global warming and climate change come in? Well, it's been known for a long time, over 100 years, that humans put more carbon dioxide in the atmosphere. We do that when we burn coal, oil, natural gas. And when we cut down forests, all those things put carbon dioxide in the atmosphere. If you put more carbon dioxide in the atmosphere, it makes the greenhouse effect stronger. It warms up the earth. So way back in the 19th century, well into the 19th century, people had a general idea of this. The first, in my opinion, really good calculation that stands up today of how strong this effect is was by this fellow. He's a Swede, Svante Arrhenius. If anybody here studied chemistry seriously, you might have heard of Arrhenius. He was a Nobel Prize winner in chemistry, not for work on the greenhouse effect, but for work he did and the rates of reactions, chemical reactions. So really foundational work in chemistry. But he also studied the greenhouse effect. And he wrote this paper, what came out in 1896. The basic results of that paper about how much warming you get from adding a certain amount of carbon dioxide to the atmosphere stand up very well today. And so this idea of the greenhouse effect, it's not a new scientific idea. It's one we've had quantitatively, I mean, with numbers, back well over 100 years. So what's happening? What's happening is kind of what we expect. We are adding greenhouse gases to the atmosphere. Some of those others I mentioned, methane gets released from landfills, from rice paddies, from leaks from natural gas wells. Part of the consequences of putting fertilizer on our crops is nitrous oxide builds up in the atmosphere, but the big one we're adding is carbon dioxide. And that comes, as I said, we call these things fossil fuels, carbon that was buried in the earth over periods of tens or hundreds of millions of years, and we're digging it up or pumping it out of the earth and burning it rapidly. We also have been cutting down forests, particularly in the tropics. We know that carbon dioxide is being added to the atmosphere, and this is probably the most famous curve in climate science. By the way, I've just mentioned, because there are links on these slides. If you want to see the data, in some cases, there are articles. I'll provide a PDF of these slides that can be posted, and then you can go and click on the links if you'd like to. Anyway, this is from NOAA, and they've been running this monitoring station top of a mountain in Hawaii. It goes back to what we call the International Geophysical Year, which was the 57, 58 period. And we see carbon dioxide has been going up in the atmosphere. It's now at a sustained level over 400 parts per million. It was, when they started the record, around 310. From samples that are confined in various places, we know that at the beginning of the Industrial Revolution, it was probably about 270 or so. So we put a lot of carbon dioxide in the atmosphere, and we're continuing to do that. Again, another topic we can go into detail on, but we know there's incontrovertible evidence that this carbon dioxide increase comes from these sources, particularly the fossil fuels. So going back to Arrhenius's work and then refinements of those calculations more recently, we expect that Earth would get warmer, and Earth is getting warmer. A number of people have done the analysis based on surface observations of temperatures. This is one from NASA, and I plotted it here in degrees Fahrenheit. If you go to their website, you'll see it plotted in Celsius. And these are variations of temperature from an average over the middle of the 20th century. We're looking at changes, not total temperature. So we're not saying it was -1 degrees in 1880. That was deviation from a mid-20th century value. And it bounces around. There's a lot of year-to-year variability, which is interesting stuff that I like to study, things having to do with El Nino events and volcanoes. There was a little upward blip in the middle of the in the 1940s. We still don't quite exactly understand why that was. It came down, it cooled a little bit. And then since about 1970, it's been bouncing around a little bit, but pretty much if you sort of take a smooth version, squint so you don't see the year-to-year variations, it's been rising pretty inexorably. This is very consistent with what we expect from our climate models. Now, the interesting question is, if CO2 hadn't been sequestered in fossil fuels over millennia, what would our climate be like? It would be a lot hotter. Actually, Carl Sagan looked at this problem, turning it around. As I mentioned earlier, the sun was weaker billions of years ago. And yet, for most of Earth history, there's evidence that there was liquid water on the planet. So how do you have liquid water with a much weaker sun? Sagan actually hypothesized that the greenhouse effect in the atmosphere was much stronger. So the question then is, what kept the climate from getting hotter and hotter and having runaway greenhouse? Why didn't we end up like Venus? And the answer is life. So the origin of all those fossil fuels, every atom of carbon and coal or oil or natural gas, every atom was pulled out of the atmosphere by a photosynthetic plant. So you've seen those pictures of the swamps of the Cretaceous, big palm tree-like things, and they would fall, and the muck was anaerobic, so they wouldn't decay, they would just sink into the ground. More recently, places in the earth, there are peat bogs. There are peat bogs in North Carolina, where carbon is being stored away by living material. And again, it's anoxic, it doesn't get oxidized. And eventually peat, which is used, for example, in Ireland and Scotland as a fuel, and eventually peat will form soft coal, lignite, and geologic processes will make it into harder forms of coal. So living things, life, the formation of photosynthetic plants, the evolution of photosynthetic plants has kept us from having a planet that was way, way, way too hot. So that's an interesting topic, and probably we can spend a lot more time on it. Probably should go on. But that's a short answer. So the warming is global. This is a map, again, in degrees Celsius from the NASA folks, comparing the temperature of the last decade with a sort of mid to the latter part of the 20th century 30-year average. Climatologists like 30-year averages. And warmer colors are hotter, and almost everywhere on the Earth is warmer. The warming has been strongest in the high latitudes in the Northern Hemisphere. And that's an interesting issue in itself. But it's warmed almost everywhere. A few places it's warmed less, the North Atlantic, that has to do with ocean circulation, but mostly you see warming, and when you see these warm colors. Because the ocean takes longer to warm up, you see the continents tend to be warmer than the oceans. And if you look at the 10 warmest years over the period of record, that's pretty reliable back to around 1880. They're all in this century, the 21st century. These are the top 10 warmest years. Different groups around the world have done the calculations of averaging a little differently. They get slightly different results, but they basically look the same. They get the same answer. So the warming is happening and it's ongoing. First of all is, can we project the future? Maybe you might have a reason to be skeptical about that, which I'll get to. But we think we can, and we've kind of shown that we can. We've been studying climate in very systematic ways. There's this IPCC process, Intergovernmental Panel on Climate Change, international collaboration of climate scientists all over the world, produce a report. A new one is going to come out next year that are called assessment reports. This is one that was done in the 1990s, and they projected climate forward. And this was their best estimate curve of how temperatures would change. It was referenced to 1765, but you could compare it with the 1900 sort of point to compare with my earlier graph. And we've observed about a 1.2 degrees Celsius change. Sorry, it's degrees Celsius again, since 1900. And this is really the shape of this curve. This curve is a projection from models, so it doesn't have all the year-to-year bumps, but it stood up very well. So we now have been doing this climate modeling stuff long enough, we can go back and see if we got it right or if we got it dreadfully wrong. Mostly we've gotten it pretty well right. So that's reassuring. Okay, but what about the future projections? This is a future projection. Again, this is from the most recent, the 5th assessment report of the IPCC. And what you see, this is the historic record with some uncertainty, and these are the projections into the future. There's a lot of uncertainty. There's this huge range of possibilities for, let's say, 2090, late in the century. Some of this uncertainty estimated comes from just natural variations in the climate. Most of those have to do with exchange of heat between the atmosphere and the ocean, as happens during El Nino events, for example. Some of it has to do from volcanic eruptions. Volcanic eruptions cool the climate. There was a couple of years cooling, about a degree, for example, after the Mount Pinatubo eruption in the Philippines in 1992. We have uncertainty about climate we still don't understand or to model precisely. So different models give different warmings for a given amount of carbon dioxide and other gases added to the atmosphere. So that's some significant uncertainty. But the big uncertainty is this green. And what's that green? That is, we don't know at all how much CO2 and other greenhouse gases we're going to put in the atmosphere in the future. I mean, at some level, this is a human choice. It's sort of a global human choice about how we choose to produce the energy we need, how we choose to power our various transportation systems. But it is plausible. They come up with these scenarios, and this one is considered plausible, which is sort of a very aggressive attempt to reduce emissions. At the top, we have what's called business as usual. We just keep pulling fossil fuels out of the ground and burning them as we have been, and don't convert to renewable sources of energy and so on. This is a huge range of outcomes for late in the century. So our children, our grandchildren, what sort of Earth they're going to be on is something that human beings, we have agency as collectively to decide what's going to happen in the future. So that's scary if you look at the top there, or encouraging because we could actually make choices to limit our warming. I think the later speakers, particularly Dr. Dello, who's giving the third talk, will talk more about this, about things we can do. But that is the big source of uncertainty. As you know, if you follow market forecasts, some of these are economic, business projections, industrial projections. People are really bad at predicting what people are going to do. And that is the big uncertainty in climate in the future. Okay, so one question you can ask is, talk about warming, does it matter? 2 degrees Fahrenheit warming that we've seen so far seems pretty small. I mean, as you know, temperatures can swing 20 degrees in a day and 40 degrees easily over a year. This is the average temperatures, highs and lows, the climate graph, if you will, for Asheville, North Carolina. And you see the big seasonal change across the year. These are averages and the big, what we call daily or diurnal change. And you saw there are big fluctuations in Earth's history and in climate. So does a few degrees matter? Well, the answer is yes. I'm going to give 3 reasons, and I'm going to focus on the last. Reason number 1 is going back to this curve I showed earlier. If you look over the last 10,000 years, we've had a very stable climate on Earth. This is the period of time in which all of our agriculture is developed, all our civilizations have been built. Using projections at the end of this graph, the current changes are very quick. So this rate of change makes it challenging to adapt to. So there were people around, but not big cities and farms and so on back in the ice ages. And the changes are fast. But then the last thing, and this is my transition to talking about weather, which I said I would, is the weather is really the important part of the climate change discussion. So this was advertised that I'd talk about weather versus climate. This is an expression you might have heard, climate is what you expect, weather is what you get. I really like there's various versions of this cartoon. I pulled this one off from NOAA's website. You look outside or you turn on the radio to decide what clothes you're going to put on. That's the day-to-day weather. But you have a collection of clothes in your closet, which are based on the climate that you live in. And so if you live in North Carolina, you probably don't have, well, maybe in Asheville you do, but certainly in Raleigh, you don't have a heavy down coat in your closet, right? Because it doesn't get that cold in the winter. The other question about weather, and this comes up a lot, is we know weather forecasts are good maybe just a couple of weeks in advance. I mean, you can take the track of Hurricane Elsa, for example. We really only nailed it down over the last week to know it was going to pass over North Carolina tomorrow. There's a reason for that was discovered by this fellow, Ed Lorenz. He's one of the great minds, in my opinion, of the 20th century. And you might have seen this picture. It's called the Lorentz butterfly. He's associated with the idea of deterministic, or just the term chaos, deterministic chaos. Chaos theory tells us that certain types of systems can just not be forecast very far in advance, because any small uncertainty in our measurements of what's going on now amplify exponentially with time and contaminate our forecast. People have done a lot of work and found the limit for predictability of the atmosphere is really just a couple of weeks. So we can't predict the weather 2 weeks ahead, but I've just told you we're projecting climate out to 2090. So what's the story with that? And that gets down very much the difference between weather and climate. I like this metaphor. Think of dice. So there's a pair of dice. If the dice are honest, each roll of the dice is completely unpredictable. You don't know what you're going to get when you roll the dice. But on the other hand, the statistics of rolling the dice a bunch of time are perfectly predictable. This is sort of a freshman or even a high school probability question. We could call the rolls of the dice the temperature, just to follow up with the metaphor. And this is the chance of getting each roll. 7s are most common. The least common rolls are 2s and 12s. And of course, you can't get higher than 12 or less than 2 out of 2 dice. And if the dice are honest, you roll enough times, this is what you're going to get. So this is a case where the climate is perfectly known, even though you can't predict in advance. I guess you could make a lot of money gambling if you could, but you can't predict in advance what any given roll is going to do. So let's extend this to climate change. This is an idea that James Hansen's a famous climate scientist. He was at NASA. He's now at Columbia University. He retired from NASA several years ago. And he said, let's consider the idea of greenhouse gas. There's various ways you can do this. The way I like to think about it, let's just take one die and add a seventh pip to the sixth. So that's our greenhouse dice. So again, the dice are still honest. Every time you roll it, you don't know what you're going to get. You're going to get a number between 2 and 13 now, which is important. But the change in the statistics is known perfectly. The average roll goes from a 7 to, we call it degrees, to stick with the metaphor, to 7.17, so rounding to 7.2. So we know exactly how the statistics, the weather is each roll, the climate determined by rolling the dice a bunch of times. We know exactly how it's changed. The weather is determined by a process that if you look over time because of Ed Lorentz's chaos, it looks pretty random. It's like the atmosphere is rolling the dice for us. So we don't know what the weather is going to be 3 weeks ahead, but we can project the climate well in advance. So weather. One of the things that happens when we add a pip is now that dice, probably the first thing you would notice that something had changed if you were just looking at the numbers coming from the rolls, is now you can occasionally get a 13. 13s were impossible before, and now they're occurring. So the biggest change you've gotten is at the extremes. That's what actually happens with the climate. So you can get big relative changes where you notice the change, the unprecedented events, like we saw 120 degrees plus in Canada, never before seen. My stepdaughter lives in Portland, Oregon. She was seeing heat she's never experienced before, and that heat wave. Those types of events, the things you notice, the thing that have high impacts on human activity, are not a small shift in the mean, 7.7 to 7.2 or whatever, or 2 degrees change in the average. It's the fact that you get more extremes. And of course, with global warming, they're hot extremes. And you can get that because you shift the distribution like we did here, or this is a smooth curve shifting the average temperature. Less extreme cold events, more extreme hot events. If the climate becomes more variable, you can get more changes, more extreme events. And then you can imagine both changing. There's this other idea, which is changing the shape of the distribution. If it loses its nice symmetric distribution and becomes skewed, you also get more extremes. That seems to be happening with precipitation, which I'll get to in just a bit. So we see this with temperatures. This is again work done at NASA, taking average summer temperatures, the distribution for different places around the Northern Hemisphere. This was the mean from 1951 to 1980, using as the baseline rather. And then you see the shifts with various decades. And this only goes up to 2001 to 2011 because that's when the work was published. You see this shift, and the big shift in the distribution is happening at the extremes. I don't want to go into detail about this, but these were events that became common, temperatures that became common, that were very, very rare in the earlier period due to global warming. So a big change in extreme heat. It's something we just expect from the basic statistics or mathematics of a bell curve or normal distribution if you shift the mean, and maybe change the shape a little, as seems to be happening. So new weather extremes should be expected and observed, not or, typo there. So they're extreme heat, and that can dry things out quickly, flooding rains and stronger storms. And a sidebar here, which I do want to mention, gets to the word exponential or exponentially. People very commonly now overuse this word exponentially. They say this is exponentially larger. The price of housing has gone up exponentially. Well, it's gone up a lot, but it probably has not gone up exponentially. But here's a case where something really does change exponentially. And what it is how much water vapor can be held in the atmosphere as the temperature rises. That's what this curve shows. This is an amplifying effect for climate change. It means if the temperature rises, we get an exponential effect. It's about 7% per degree Celsius warming. And that means if there's more water vapor in the atmosphere, you can get much heavier rains. The heaviest rains can be heavier. And when things are dry, that means that's the extent to which the atmosphere wants to get water from the ground. So things can dry out a lot faster. So we can get extreme heat and you can get very rapid drying. People have started using the term flash drought as the counterparts of the older term flash floods. You can get stronger flooding rains. This is a picture from my local newspaper from a few years ago from a summer rainstorm. It turns out that can also cause stronger storms as well. So let's talk about heat. Once the ground dries, the sunlight striking the earth, if it's cloud-free, that energy doesn't evaporate water, it just goes into making it hotter. So once things dry out, the heat can build up much faster. Here's a schematic of that that shows the dynamics. This was a paper that was written in reference to the 2011 Russian heat wave. And we're seeing this happening, and it's also most acute in our cities, because in the cities, heat is stored overnight in the concrete and the buildings, and we don't have the compensating cooling effect from water evaporating through plants, what we call transpiration. So vegetation keeps things cool. Impermeable surfaces, unvegetated areas heat up more, and cities store heat overnight. So we see, and this is from the US Global Change Research Program, that over a period of time, we're seeing decade by decade greater heat waves. And urban heat waves, people focus on the temperatures at night, actually, the lack of cool temperatures overnight that have the greatest public health impact. And we're seeing the season in which these extreme heat events getting longer and longer. Each of these refers to an urban center. So we're getting more heat waves in cities. We expect that, and we're also getting faster drying, and we expect that as well. Again, the extremes have the greatest impact, and it's amplified by this exponential effect of the atmosphere, in this case, wanting to evaporate more water more rapidly. The flip side of that is when it rains, the atmosphere can hold more water. And so we see heavier rain from everyday storms. These are statistics of days with the precipitation above 3 inches in the Southeast United States. Decade by decade, it's very noisy. Rainfall varies hugely, but there is clearly an upward trend. And when you look at station by station, some have seen a decrease because it's a very noisy record. There's a lot of variability in the atmosphere, but more stations have seen increases. You could also look at the frequency of precipitation events that occur in what's called the 5-year recurrence interval, the 5-year rain. And again, a lot of variability, but those are going up with time as temperature warms in the United States, as we expect. So we're getting more extreme rains, and then you can, of course, point to anecdotes. I happened to grow up in Maryland, north of Washington, D.C., so I visited this place, Ellicott City, which is a lovely town on the Patapsco River. They had so-called 1,000-year floods, separated by a year in 2016 and 2018. That's a picture of flooding at downtown Ellicott City, historical town. And you can find many, many examples like that, just was salient to me. So we're seeing these effects. The impactful result of climate change is much more at these extreme events than it is in how much temperature changes. Hurricanes. So we've always had hurricanes. Hurricanes have always made landfall in North America. But in terms of the rain, we're seeing as the oceans have warmed, and this is the ocean temperature anomalies associated with Hurricane Florence, and Hurricane Florence produced huge amounts of rain in North Carolina, not so much out where you are, I guess. And this is work by a colleague of mine based out at Asheville, although he works for NC State University. In terms of the volume of rain going back 50, 60, or 70 years, I think, their recent storms. Number one was Hurricane Harvey, which produced dreadful flooding in the Houston metropolitan area in Texas in 2017. And then Hurricane Florence was number 2 in 2018. And again, it's this exponential amplification of the effect of a warmer climate and warmer ocean temperatures. The water that rains on us from a hurricane comes from the ocean surface, but it's warmer, more water evaporates, and we get heavier rains. Now, it turns out that rain condensing in clouds and hurricanes is the fuel that produces the winds in hurricanes. And you could think of them as a heat engine. This is work done by this fellow, Kerry Emanuel, who's one of the world's expert on hurricanes, tropical cyclones. He's at MIT. This is a nice diagram. I won't go into the details of it. Basically, it says the hurricanes are a heat engine. How much energy they can produce is driven by the difference in temperature between the ocean surface and the temperature at the top of the cloud layer. And if that temperature difference increases, hurricanes can generate more energy and they can get stronger. The strongest ones can get stronger. Not everyone will. He developed a measure he called potential intensity. Some hurricanes do reach their potential. The number of storms varies from year to year for lots of reasons, but the proportion of storms that become major hurricanes, so Cat 3, 4, and 5, is increasing with time. This is analysis done by Jim Cousin, who works for NOAA. He's actually based in Madison, University of Wisconsin, but works for NOAA. So we see this upward trend. And it's what we'd expect from Kerry Emanuel's theory in a warming climate. So these things are all consistent with pretty basic understanding of statistics and physics based on an understanding of the greenhouse effect, which really goes back to work of Arrhenius over 100 years ago. I wanted to leave time for questions, so I'm going to sum up. What are the takeaways, if you will? I would say our wild climate history shows that greenhouse gases, particularly this one, CO2 is important in Earth's climate history. We're adding CO2 to the atmosphere, we being the human race. That's producing warming as expected, but the most dramatic effects of that warming, the ones probably that have the greatest economic impact as well, are greatest threat to life and property, are in the weather extremes. What we expect and what we're seeing is more severe heat associated with more rapidly occurring droughts, heavier rains, and stronger storms. These are things we're already seeing happening, and we should expect and anticipate and prepare for them to amplify as Earth gets warmer. Two last things, two more slides, I think. One is a set of resources. A lot of what I've just talked about in the applications to North Carolina is in the North Carolina Climate Science Report that came out, 2 years ago now, I guess. And that's where you can get it online for free. For your gardeners, there's this wonderful book. It's a decade old, but I think it's really still pretty current, published by the Brooklyn Botanical Garden, which if you get to New York is a lovely place to visit, called The Climate Conscious Gardener, which is both impacts and things you can do as gardeners to address climate change. You're going to hear the next two talks that are from people from the State Climate Office, which is just an amazing resource online for anything about North Carolina climate. That's a snapshot of their website, their front page. And then not the subject today, it'll come up later. If people want to know what they can do, I like to refer to them to this Project Drawdown. There was a Project Drawdown book or book called Drawdown that came out several years ago, but they constantly update it for all the things we could do at all different sectors of human activity that will reduce the growth of greenhouse gases in the atmosphere and actually draw carbon dioxide out of the atmosphere. Finally, these are the next two talks. I know both of these people and they're great, so they'll be good talks. Rebecca Ward is Assistant State Climatologist from the State Climate Office. She's going to talk about climate change in North Carolina mountains. And I think she'll talk a lot about sort of the nuts and bolts of what determines our climate in North Carolina, particularly in your part of the state. And then the State Climatologist and Director of the State Climate Office, who just joined 2 years ago, Kathy Dello, is an amazing person, an amazing leader for that climate office. She came from Oregon, actually, so it's great we got her in North Carolina. And she's going to talk about things you can do. So that's the end of my talk. I see there's a question already. So net rainfall increasing, droughts can be more frequent for shorter. Well, turns out it really depends on where you are on the planet. Most of the water that cycles through the climate system is cycling in the tropics. Remember, about half of the Earth surface, or exactly half, is between 30 degrees north and 30 south latitude. So basically in the tropics. So there it is definitely true. There'll be more evaporation, more water cycling through the system. For example, the tropical rain belt called the Intertropical Convergence Zone will produce more. But that drives a circulation called the Hadley cells. And the Hadley cells, the descending branch, are where Earth's great deserts are. So it is likely that the descending branch of the Hadley cell will actually expand and get drier. So there's an expansion expected of the subtropical dry regions, that those will expand away from the equator. Places we already see that happening that will get hotter and drier, the Mediterranean basin. There have been severe droughts with huge implications for politics and national security around the Mediterranean basin. The collapse of Syria, for example, as a functioning country was triggered to a large extent by a very, very severe and persistent drought. We're seeing drought increasingly in the Southwest United States. Lake Mead behind Hoover Dam is the lowest it's ever been. They're predicting limitations of water supplies in the Colorado River. That's part and parcel of this change. So it's a little bit of a cliche in our climate business is the rich get richer and the poor get poorer. So wet regions get wetter, like that intertropical convergence zone, tropical wet zone, and other regions, dry regions get drier. Now, if you're in North Carolina, it's likely that the mean rainfall will not change a lot. But because when we do get heat, things can dry out a lot faster, we may get both a flashier rainfall regime where we get longer regions between rainstorms, but when the rain does, it'll be heavier. The mid-latitudes are a little complicated that way. In North Carolina, of course, we also get rain from hurricanes, and we're already seeing that those rainstorms are getting stronger. So places that get tropical cyclone rains, we'll see heavier rains. So it's kind of a mixed bag. In high latitudes, it'll probably get wetter. So those regions will get more of their precipitation as rain instead of snow. And that has implications for water supply as well. For example, in the Mountain West, if you get more rain over the year, but if it rains in the winter, then it just runs off, and they rely on their winter snowpack as a reservoir for their water supply in the summer when things get drier. That's not going to work as well anymore. And we already see that happening with drought conditions in the West.
This has been an amazing program. You've certainly made some new information to consider and think over. You know, your explanation's been really straightforward. Outstanding program.
Oh, well, thank you. Well, thank you for your attention. And the last thing I would say, that's why my email is there, and I will provide these slides. If you have a question about something related to climate, I may not know the answer, but I probably can point you to someone who has the answer. Feel free anytime to email. Just like extension, I'm very fond of North Carolina State University being a land-grant university, and I consider doing this sort of stuff part of our land-grant mission. So I'm always happy to answer questions about climate and climate change.
Thank you so much. Thank you, everybody, for joining us. Have a good evening.